Okay, I think we'll get started. Hopefully everyone can hear me. And I'm sharing some slides here, the same slides that I've been scrolling through, but just to start off today, I'll start by introducing myself. Christina Tabakhorst, the Southeast Iowa Ag Engineer for ISU Extension. Housed in Johnson County, serve 21 counties in Southeast Iowa. And just to start by thanking everyone for being here today. I know it's kind of unusual circumstances, but we're really glad to get attendance as we try and do field days online. So yeah, we're doing a series this week, and hopefully we can bring you some useful information. So let's see. So as a couple reminders before I introduce our speaker today, we'll be using the Q&A box, the question and answer box for questions. So as you're going through, if something pops up that you think to ask, use that Q&A box. Can everyone still see my slides?
No, we cannot.
Okay.
There we go.
Now you can? Okay. Okay. So a reminder to use the Q&A box. If you can't see it, you might have to hit the 3 dots button to bring that Q&A box up. But the panelists and myself will be checking that Q&A box to see if it's something we can answer through the presentation. But most of the Q&A questions will be answered probably at the end of the presentation. We might put in some links for you guys in the chat box, but we'll mostly probably use our Q&A box. And as a reminder, if you need the CCA credits today, if you did not with registration put your CCA number in there, you can put that in the chat box and send that to us, and we'll get that registered. And as a reminder, similar to yesterday, this field day series was brought to you by your Extension Farm Management Specialist, Ryan Droletti, your field agronomists, Virgil Schmidt, Josh Mickle, and Rebecca Vidito, and then your research farm staff, so Chad Hasseltine, Cody Schneider, Myron Reese, and Dominic Schneider. And also your board members. So board members were responsible for picking the topics, and they really wanted to hear Mike's talk today and talk about the tile drainage study that's going on at the research farm. And we are offering the CCA credits today, so as a reminder, make sure you had that taken care of. And then also as a reminder that this is a series, so we did the first one yesterday, and then we'll have 2 more yet this week. And we are recording these, so they'll be up on the ISU Crops Team YouTube channel. So to get into today's topic, we have Dr. Mike Castellano with us. And his topic today is utilizing tile drainage to better manage nitrogen and improve corn yield. So Mike Castellano is a professor. He's in the Department of Agronomy. He's also an advisor. He was one of my advisors in grad school. So I'm really excited to have him here today. He's kind of the nitrogen cycling expert, as I really think of him for sure. So I'm going to pass it on to Mike. So I'm going to stop sharing, and then he should be able to share his slides. Okay. Looks
okay. Thanks, Christina. Everybody can see the slides okay?
Yep.
Great. Yeah. So thanks for inviting me to speak. We've done a lot of work in Crawfordsville now for really almost the past 10 years. And it's always a pleasure to work down there despite the drive. So I want to begin by just highlighting that the Southeast Research Farm has a really unique resource in its drainage intensity experiment. So right as you pull into the farm there, on the right side of the road is is an experiment where there are individual plots that have no drainage, shallow drainage, conventional drainage, and controlled drainage treatments. And this is it's a really fantastic experiment and relatively unique, and I'll come back and talk about that in a few minutes. But unrelated to that, about 5 or 6 years ago in the state, we have been doing some work trying to look at the variability in the optimum nitrogen rates that we find. And obviously, everybody's aware that, you have a different field, different year, different optimum nitrogen rate. It's really tough to predict. I wouldn't be here right now if it was easy to predict, probably. And so we were trying to really sort some of that variability out from year to year and field to field. And one thing we noticed was that fields with shallow water tables or poorly drained soils tend to require more nitrogen fertilizer for the maximum return to nitrogen, or the optimum fertilizer rate, whatever you want to call it, than well-drained soils. In other words, well-drained soils require less fertilizer, oftentimes despite higher yields. And so we recognized Crawfordsville, the Southeast Research Farm, as really an excellent place to test this hypothesis and see if it bared out on the plots. And so that's what we did. We took these plots with and without drainage, the different drainage intensities, the controlled drainage, and we basically ran nitrogen fertilizer rate trials on them and empirically identified the optimum nitrogen rate in these different treatments. And so I'm going to talk a little bit about the results of that work today. We've begun to publish some of that stuff. We'll be continuing to publish those data in scientific and extension publications going into the future. And let's see. And so that's really where I want to begin. I also want to highlight, though, as we talk about this drainage stuff, I saw Steve Berger is in attendance here, and another important part of this for me that led me to think about this stuff more holistically, or from more of a systems approach, as I like to call it, was I was down on Steve's farm doing some work, and I wanted to. I think he's okay with me sharing this story. I know Steve's a pretty open guy about this stuff. I was down on this farm doing some work on soil health, and I wanted to share some results with him. And I said, well, why don't I come down after harvest and everything's wrapped up, Steve? And he replied to me, Mike, I spend a lot of time after harvest installing tile. I've got my own plow. And that really was a changing moment for me as a scientist. And really, I highlight it because it's those interactions I get to have with farmers out in their fields that really kind of spur, I think, my best ideas and my best work. And that was really a game changer for me when I realized how important tiling is to Steve, even though he's not on the Des Moines lobe, which is kind of how I viewed that stuff in the past. So thanks, Steve. A lot of this work today that I'm going to show can be attributed to some of the ideas you spurred in my head. So I'm going to talk about sustainable intensification of tile drainage here. Sustainable intensification is a UN Food and Agriculture Organization term. Basically, it means producing more with less. So the goal here is to produce more crops with lower environmental impacts is the goal. So you want to think about that as 200 bushels per acre with 30 pounds of nitrate loss versus 220 bushels per acre with 15 pounds of nitrate loss per acre. So as we all know, we have some pretty poorly drained soils, not only in north central Iowa, but in southern Iowa and southeast Iowa, and all throughout the Corn Belt, as you can see, Ohio, Minnesota in particular, Indiana, and Illinois. We all benefit from tile drainage, and it's really not just benefit. We wouldn't be here if it wasn't for tile drainage. I think population and economy-wise, we would look something more like central, South or North Dakota. Without the tile drainage that we have, we'd be a swamp. Here are some modeled water table data from our FACTS project that is online. It provides some data for folks to look at about how the current cropping season is going in terms of things like water table, soil water amount, growing degree days. And here we just have the depth to water table. This was from last spring, and you can see, we all know it was a really wet spring. It's within the top top foot rather of the soil in most of the state at that time. And so, because of these things, we've had drainage in Iowa for quite a long time. It was installed about over 100 years ago, and this is really key here. I want to highlight this article from the New York Times that talks about the installation of drainage in our state because of a couple things. One, it highlights that farmers paid for the vast majority of this infrastructure. Right now, we would put the value of the Iowa drainage infrastructure somewhere between 10 and 100 billion dollars. That's 10 to 100 billion dollars in present money. It's really a remarkable piece of infrastructure, and we've got to pay attention to it more. And I think better manage it as a state and a community. And I'll talk about that a little bit more. But really today I'm going to focus on the biophysics of this system. So I think another thing to point out that I'll touch on a little bit today is that this infrastructure was also installed 100 years ago when Iowa was a significantly drier place. And so what happens when a system gets wetter? We need more drainage. And a really key part of this is that we know the rate is a little bit less than optimum drainage rate for economic return is a little bit less than the optimum drainage rate for maximum productivity, because at some point a narrowing of drains, it'll further increase yield, but not enough to pay for that further increase in narrowing of drains. So it's really susceptible to increases in wetness, environmental wetness. That's kind of the point I'm trying to make there. So today I want to make three main points about drainage. So first is that drainage is not incompatible with water quality. Second, drainage creates large improvements in nitrogen use efficiency, and in the long term can reduce agricultural greenhouse gas emissions. And three, climate change is leading farmers to expand and intensify drainage systems, and that really creates an enormous opportunity to benefit both productivity and environmental quality in our state. I really think drainage can be a key to addressing our nutrient load challenges to the Gulf of Mexico and also locally at the Des Moines Waterworks. I think better management of our drainage infrastructure is really a win-win solution for everybody in the state towards those challenges. And I'll discuss that a little bit today. So first, just thinking about drainage and water quality. So as I mentioned, the drains were installed over 100 years ago. The Des Moines Waterworks has one of the longest nitrate monitoring records on Earth, if not the longest. We think it may be the longest, actually, going back to about the 1940s. And what we know is that nitrate levels at the Des Moines Waterworks did not begin to increase until the early 1980s, late 1970s. So decades after the drains were installed, right? Decades after the drains were installed. And that's not a delay in the amount of time it took the nitrate to travel down those drains to the Des Moines Waterworks. What it really demonstrates to us is that it was the change in cropping system from a perennial small grain corn cropping system back in the pre-1970s, 80s era to the corn soybean, the annual cropping system we have now that has long periods of fallow during the year. It's those long periods of fallow in the spring and fall that really drive the nitrate loading that we have in the state. It's not the tile drains. Another piece of evidence is there's been some fantastic work in Minnesota. I saw Shane Bujeha is on the call today up in Minnesota. He's an extension agent up in Minnesota. Some fantastic work on the Des Moines lobe there by the University of Minnesota in drainage monitoring plots showing that even in really well-drained plots, if you grow alfalfa on them, there is virtually no nitrate leaching whatsoever. And it's because the alfalfa uses all the water and nitrate because it's a perennial crop. When the soil starts producing nitrate in the spring, the alfalfa starts taking it up rapidly, and as a result, there's no nitrate leaching, despite the fact of having those drains underneath the alfalfa. We know alfalfa requires good drainage to grow, right? It's one of the most sensitive crops to wet soils. The second point here, drainage creates large improvements in nitrogen use efficiency, and in the long term can reduce agricultural greenhouse gas emissions. So here we just have kind of a biophysical conceptual model for the effect of drainage on the nitrogen cycle. And I want to use this today to communicate how we can get higher yields with drainage. We know we wouldn't be putting in drains if it didn't increase yield, right? So how can we get higher yields, but also increase nitrogen use efficiency and reduce nitrogen fertilizer inputs, right? So what we're saying and what we've learned from our research at Crawfordsville is that despite having greater yields in the more intensively drained plots, we can actually get those yields with lower nitrogen fertilizer rates. How does that happen? And so here on the left, we have a poorly drained system or no tile drains. So here we are, this is a conceptual model for the system without tile drains. On the right, a conceptual model for the system with the tile drains. And what you'll notice is that one thing the tile drains do is reduce the total amount of soil organic matter. And so oftentimes we view that as a bad thing, right? Because soil health is often positively associated with soil organic matter levels. But I really want to throw some caution to that, because it's not so much the amount of soil organic matter that's in the soil, it's the cycling rate of the nutrients through that soil organic matter that's important. We don't want huge pools of soil organic matter. We want fast rates of nitrogen cycling through our soil organic matter. And so the reason we have the high soil organic matter in the poorly drained soils, think about them as a wetland, right? That's where we have high soil organic matter. It doesn't cycle. It doesn't cycle. That's why we have those high pools, right? We're just continuing to put everything we put into the system into the soil organic matter instead of making it available for the crop. On the right side here, you can see when we put the drains in the system, yes, it reduces the soil organic matter levels a little bit, but it also increases the rate of nitrogen cycling. So now instead of having to put nitrogen fertilizer in your system because there's low cycling, the soil is providing a lot of that nitrogen for you, right? We know our soils have 10,000 pounds per acre of nitrogen on average in these really good soils that we're cropping. And 2 to 5% of that becomes available as nitrate every year for the crop. And the more that becomes available and the less that's lost to the environment, the less fertilizer we have to invest in to put on our fields. So that's kind of a concept model of what's going on. Another important piece of the lower nitrogen fertilizer requirement that I just mentioned is those lower environmental losses. And so on the left here, yes, we have less nitrate leaching because we don't have the drains, right? There's no doubt about it that the drains do exacerbate nitrate leaching in our annual based cropping system. On the other hand, though, we have a lot less denitrification losses in the well-drained system on the right than the poorly drained system on the left. And this is a really critical point because I think the amount of nitrogen loss to denitrification is often underestimated. It could easily be just as much as the nitrate leaching from the system. So those are a little bit of the biophysics here. And then I want to highlight the agricultural greenhouse gas emission part, because this is a piece that's beginning to get a lot of press down in Southeast Iowa in particular, with Mitchell Hora's great work down there on soil health and some of these carbon credits that may become available. So here, while on one hand the drains reduce the soil carbon stocks and the soil organic matter, soil carbon stocks, and that'll put CO2 into the atmosphere in the short term, that loss is finite. We know the way soil organic carbon changes is you go from one level to another when you improve the drainage. You don't continually decrease over time. It's a re-equilibration from a high level to a relatively lower level. But then it re-equilibrates. It's not a perpetual loss, in other words. On the other hand, we get huge reductions in nitrous oxide emissions, which is a powerful greenhouse gas that's associated with fertilizer inputs. And so to put that into perspective, 1 pound of nitrous oxide emissions from a crop field is equivalent to 300 pounds of CO2 emissions in terms of the heat trapping potential of those two gases in the atmosphere. And so when we improve the nitrogen use efficiency of the system, though, so that we have to put less nitrogen fertilizer on for more yield, that loss is perpetual. Every year that the drains are there, we can put less fertilizer on, and eventually those avoided emissions, we call them, in avoided nitrous oxide emissions, will catch up and surpass that amount of CO2 that we put into the atmosphere by improving our drainage systems. So that's a kind of the third point I wanted to make about the greenhouse gases there. So I want to highlight here on the yield side too, as we think about environmental quality, the drains, they impact crop yield not just directly by improving root growth, as we see here, and improving photosynthesis of the crop, but they also improve crop growth indirectly. And I mean, I think that's something that farmers are very familiar with, right? It allows farmers to get into the field and maintain plant health, manage soil in a more timely fashion. But what it also does, of course, is it provides more confidence in the implementation of important conservation practices, like reduced tillage, for example, and cover crops. And as we've been talking about this, you know, and we knew theoretically this was possible from our model simulations, a number of farmers have kind of come up to us after the presentation and said things like, geez, if I didn't have the pattern tiling in my field, I'd never be able to do the strip tillage and cover crops that I'm able to do. And those things, you know, the strip tillage, the reduced tillage, and the cover crops, the effects they have on nutrient loss reduction, the positive effects they have on nutrient loss reduction far exceed the negative impacts of the tile drains on that system. So really, this intensification of drainage, it allows more conservation practices, perhaps counterintuitively in some cases. Okay, so I want to wrap up real quick here by, you know, talking about the work we did at Crawfordsville. So what we did with those nitrogen rate trials, we measured the yield and environmental impacts associated with them over time. And then we put the data into a simulation model and we simulated the processes. And what we found was that, you know, the drains reduced the many of the environmental impacts, like nitrous oxide emissions, denitrification, reduced the agronomic optimum nitrogen rate here, reduced the global warming potential of the system. They increased the nitrogen mineralization, maximum root depth. They did increase the nitrate leaching, of course, though, right? We knew that was going to happen. And so what we think going forward in the future is going to be important is coupling the improved drainage or the intensified drainage with conservation practices, such as cover crops, and also edge of field practices, right? So drains offer an opportunity to reduce nitrate losses that we don't have in undrained systems. And those might be denitrification bioreactors that are put at the end of a collector drain and the field drains, or denitrification wetlands at the bottom of the main drains here. These are just some simulations here. I don't want to get into the details very much other than let's just look at panel F here. And what you're looking at here is we simulated these systems over 35 weather years using historical weather records from Crawfordsville. And so what this is saying is that, you know, most of the time, the drain system in blue, you know, roughly 40% of the time, it's going to have a much higher yield than the undrained system. But there will be years when the undrained system does perform better in drought years, for example. So it really highlights the point that, you know, we have to have a dynamic management system going forward. We can't manage for the average. If we continue to manage for the average, we're going to perform at the average, and that's not what we want to do as a state, right? And so all these ideas here that we talk about are in this paper that we published last year. And just some alternatives here going forward that we discussed: the wetland saturated buffers, shallow drainage, controlled drainage. Some of the simulations here that we have up on the web, I'd urge everybody to look at this website where you can see up-to-date nitrogen mineralization data. And then going forward, we're going to continue with some of this work. We're putting in more of these drainage intensity experiments so we can figure out what's going on and try and guide these nitrogen fertilizer rates with better confidence as a function of drainage, and look at how the drainage can impact the environmental quality of our systems as well. So with that, I'd be happy to take any questions. Christina, I'm not sure where you want to go from here.
Yeah, so I guess if anyone has any questions for Mike, feel free to put them again in the Q&A box. Mine shows up on the bottom banner there. Otherwise, you might have to hit the 3 dots to find more and find the Q&A. So if anyone has any questions, go ahead and enter those. But I guess I'd kind of start off with one. This is a really broad question, Mike, but I know this work you've done in sustainable intensification. What are some of the, I guess if you had to give a couple points to people that are working in kind of the tile drainage water quality field and farmers out there making decisions on whether or not to install more tile drainage and how to do it, I guess what are some of the big things that you would recommend that as a state in the Midwest in general, what we need to think about as we are intensifying or putting in more drainage? What are kind of the big things you hope we kind of focus on as we do that?
Yeah, Christina, thanks for that question. That reminds me, I've got one last slide here that I didn't get to, but it kind of addresses your question about what we might want to do going forward. So shortly after we published this paper here, we got together with IDALS and IAWA, and we put together a NRCS RCPP grant proposal based on this idea of conservation drainage, or the intensification of drainage. This project was funded, which is fantastic. The NRCS is going to contribute $10 million, partnering contributions over $20 million for the state. This is going to offer a lot of opportunity for many of the folks on today's call to implement some of these practices, receive technical assistance and financial assistance to put in some of these conservation drainage practices, we might call them. And so some of the things more specifically that we've discussed are things like shallow drainage, where we can increase the drainage rate, so the rate that the water leaves the topsoil, but not the amount of water. That's important. So it's the depth of drains that really regulates the amount of water. That's an important piece of the puzzle, I think, because it's the amount of water that goes downstream that regulates those nitrate loads, not the rate of drainage, but it's the rate of drainage, of course, that's important for getting in the field. I know that's obviously, there's a lot of constraints on putting shallow drains. It's not just as simple as saying that. I know that, but that's one thing to consider. I think other things to really consider, though, and that this USDA funding is going to help our farmers with are some of these edge of field practices, like putting in wetlands at the end of the drainage mains. Going forward as a state, I would like to see some incentive programs for this. I think that's really important. So we all benefit from these denitrification wetlands, right? It adds some diversity to the landscape. There are most effective practices, among our most effective practices, if not the most effective practice for reducing downstream nutrient loss. They only take 1 to 3% of the total watershed to put in, and they can reduce 70% of the nitrate loading from the watershed. I mean, that's a really remarkable thing going on. But again, it's not that easy. They're extremely expensive up front. although over time, the per pound of nitrate loss reduction becomes the cheapest. They're expensive up front. We need some money. There's also some regulatory problems associated with them. So oftentimes, if we're going to improve that main drain capacity, the drainage coefficient of that, we have to do wetlands reassessments upstream and perhaps mitigate some farmed wetlands. I think that's unfortunate, given that they're farmed wetlands and they've been farmed for decades. Why not waive those mitigations if we're going to put that wetland in at the bottom? So I think there's some policy issues to think about there. I think those are the main, some of the main action items I'd like to see. I hope this project with the NRCS, not only does it provide technical and financial assistance, but I hope it really creates some interactions between policymakers, farmers, managers, scientists, so we can really find some solutions going forward that help get these conservation practices on the ground. I think, like many things, we know what works, but we need help getting it in place.
Yeah, that's great. There's two other questions. So one, with the addition of denitrification bioreactors or wetlands, will the total denitrification with intensified drainage be equal again to undrained systems?
That's a good question. I think we can get very close. And I want to highlight that undrained systems, it's not so much that they don't lose nitrate. It's the travel path is longer from the field to the stream. And so they do lose less nitrate because of that, but it's not because they're not losing the nitrate from the nitrogen from the system. It's that there's more opportunity for removal or retention between loss from the root zone to the time it gets to the river, for example, right? And that might be denitrification to the atmosphere. It may be a mobilization in the soil organic matter. It's likely both of those pathways contribute. The drainage systems kind of just speed that up. So I think it may be possible, and this kind of gets back to the point I made about the alfalfa experiments in Minnesota on the Des Moines lobe, where they showed that despite having drains with a perennial crop, there's no nitrate loss from the system. That's also been demonstrated in Iowa with perennial grasses under biofuel systems in Ames, a system called a comparison of biofuels experiment. They have fertilized and unfertilized perennial grasses in drained fields, and there's no nitrate loss from them, despite the fertilization even. And so I think that speaks to the fact that these practices can be exceptionally effective in reducing nitrate loss. So I think we can get back to where we were.
Okay, I think the last question we'll take. Would controlled drainage systems narrow that yield gap during drought years?
Yeah, there's good evidence to suggest they would help with that. This is some important work. I haven't gotten into this work personally, but I know Matt Helmers in particular is doing a lot of work on this this water recycling. So not just controlled drainage, but also collecting the water in the drains and using it later in the year. Speaking about the policy initiatives, Christina, that I'd like to see reconsidered, one of them would be drainage water recycling in those wetlands. So, for example, if we have a wetland, a denitrification wetland that's been partially funded by USDA, that's received cost share, that water can't be used to irrigate later on in the year. But I think that's a mistake, because that wetland, 90% of the denitrification that it does, 90% of the nitrate removal is going to occur in the spring when nobody wants the water, right? And the denitrification is really, it's done by the time we want to take that water and put it back into our fields. So on one hand, we're not going to get any nitrogen out of it, but that's fine. That's not what we're looking for. We're looking for the water, right? It's done its job by that time. And so I think there's good scientific basis for recycling that water, and we should lift, or USDA should, I think, reconsider that policy.
Okay, well, I think we're probably at the time to wrap up. And just to note, in the chat box, Rebecca did put the link for where all of these recorded webinars will be posted if you missed one. If you missed one this week, want to go back and look at it. But yeah, I just want to finish by thanking everyone for joining us, and really thanking Mike for being here to talk about some of this stuff, and especially some of the stuff that's going on at the research farm in Crawfordsville. So with that, don't forget your CCA credits if you haven't done that already. And thanks a lot for joining us, and be sure to tune in tomorrow as well. So.